Ouais. Bonjour à tous. Hello everyone. So this one is a presentation about implementing ray marching for drawing signed distance functions in a shader, in a pixel shader, for absolute beginners, which includes me, because I was curious of how a signed distance function is drawn in 3D. And that was a topic coming from a discussion with young Marex, who also was curious, was starting 2D shaders, and we were discussing about 3D shaders. So in the beginning, we didn't exactly have the compute power to draw shaders or to draw anything that requires a lot of compute power per pixel. So instead, we were drawing in the other direction from 3D geometry to screen pixels by drawing a small number of 3D objects into many pixels, like one line for wireframe rendering. One line has just two vertices in 3D, and it generates all the pixels in between once projected in 2D. So on the left, you have hidden surface removal, but essentially, all that is drawn is just the lines. You still have to erase the picture in one way or another. In this case, it's not even hiding. It's rendering lines through everything through facets. So there's not even any hidden surface removal. It's just wireframe rendering. So all games from the 80s. This is an example of CAD hidden surface removal, again with just the lines. And when it's shaded with flat shading, but with just lighting, you get this from this CAD model for a part, for a 3D printed part. So this is done by drawing triangles, projecting the vertices of a triangle, and then filling the triangles in the 2D screen. So that's how it used to be done. You have a camera, you want to compute how lines from the camera to each vertices of a 3D object intersect a virtual screen that's really exactly the same thing as the film in a film camera or the sensor in a digital camera. And so the point is to find those 2D coordinates on the screen by applying a 3D projection algorithm. So this is your screen space, that's what you want. And this is what you have, your object space or scene with your 3D objects. So essentially you want to compute this in along the z-axis from the camera. You want to compute the 2D x and y coordinates from the xyz coordinates or vertices in 3D space. So if we reduce this to just a side cut of what happens, now the screen space is just this vertical line, and what we want is the height of the projection of some 3D space vertex into this particular coordinate along the z-axis. So from camera to screen, this is the focal length. And computing this is just a simple case of Thales theorem, where this divided by this is the same number as this divided by this. So if you shuffle around those coordinates, you move this divided by focal length here, it just multiply by focal length here. So essentially your y coordinate here, this one, projected, is focal length times the original y coordinate divided by the distance to the object. So this is the equation you will have in as many coordinates as you want. So it works for x and y. For projecting, for doing what is, I forgot to mention, this is called the perspective projection, because we want objects that are further in the distance to be smaller. This is what the human eyes or a regular camera does in the physical world. So this is the one we will be using. So when we work this way, we project the object space to the screen space, and then we draw 2D primitives. So we do not very many 3D computations, 3D projections, and we do a lot of 2D pixel filling. So the algorithm, to summarize this, and many links for how to do rotations and translations and moving the camera around. But in the end, it's what I just showed. So for each triangle, because all geometry can be reduced to triangles. The reason to reduce everything to a triangle, including spheres and whatnot, is that three vertices in space, like the three vertices of a triangle, they define a plane in 3D space. So it means that there cannot be any skew. Whereas if I try to do a square, if those four vertices are not in the same place, my square could be skewed. That is, it will look like a saddle, you know, like a horse saddle. And so it's no longer obvious what to draw in 2D space, whereas one triangle in 3D space, it will always be a triangle in 2D space. And so that's the simplest thing to draw. I mean, the drawing of one triangle is trivial. The drawing in practice is this second part, where essentially since your computer screen is organized in rows, in lines, for each of the lines, let's say if we take this triangle, once we have the 2D coordinates, we progress along the lines. Every time for one line of the screen, we compute what is the intersection of the line with the edges of the triangle, and that gives us one horizontal line, and rendering an horizontal line in a computer video memory that is also by lines, it's just filling adjacent bytes of the screen. So that part is trivial, and that's why it's fast. So that's what we could do on an Atari and Amiga, purely in software, in the case of the Amiga, assisted by the blitter, but still not something very fast. So this is really drawing from object space to screen space. That won't work if you don't have a geometry. So like those essentially mathematical surfaces, or if you have objects that repeat periodically to infinity, you just cannot handle an infinity or a very large number of triangles. So that won't work. So you cannot draw objects that go to infinity or that are infinitely detailed, like like a fractal would be. That wouldn't work. So yeah. So those, again, come from various demos. The demos that actually pretty much, apparently, for what I could find, introduced these notions of drawing those infinite objects or infinite details. Actually, that's fairly recent technique, because pretty much you will see in the rest of the presentation that you need something like the parallel calculations of a GPU in order to draw that. And we didn't have those in computers before about 2000. So this is actually probably still in software, because that's from 2001. Lattice by S3C. This one, 2006, this is clearly done with a shader, with GPU. But still, that's among the early ones. So this one, 2003, that's also an early one. Aura for Laura by Sopadopa. So we want to do the opposite. Rather than going from scene space to screen space, from geometry to the camera sensor, if you want, we want to do the other thing. We want, for each pixel that we need to fill in the screen space, we want to interrogate the scene. What is the 3D object that is seen, visible through that one pixel of the screen? And that's, of course, the one that is on an axis. Well, sorry. I'm going slightly faster than I should. The other thing we want to do, so I will have an illustration for what I just said, but the other thing we want to do is that we want to work with a scene that is not composed of triangles, that is explicit geometry. We rather want to be able to work with something that is called implicit geometry, geometry that is defined by typically mathematical functions. So like this thing called a hyperboloid, which is like a hyperbola but in 3D space, the 3D generalization of a hyperbola curve. So it can look like that. It depends on the parameters, of course, that you put in the equation, but it can look like that. Of course, that actually extends to infinity, and the question is, how do we interrogate this mathematical object in order to find which of the pixels, which pixel screen goes through this picture, this object, I mean. So that's actually what ray tracing wants to do. So this is actually a variation of ray tracing, what we want to do. But the typical mathematical representation we want to use here is not this kind of equation specifically, but it is a mathematical construct called the signed distance function, where from one point in 3D space anywhere we want, so typically our camera, it gives us the distance that's closest to our point in 3D space to the object that we interrogate, so the object for which we have assigned the distance function. So we don't know which point on the object is closest to us. So let me give you an example. If I was interrogating this as a signed distance function, let's say, you know, from the extremity of this axis, the thing that is here. So, well, no, I'm going to cheat a little. I'm going to say from here, or from here. Actually, it's easier to see because of the lighting. So here it's fairly obvious that it's probably going to be the point that's right here along the angle. However, if I interrogate from here, it's going to be, you know, slightly aiming up. So we don't know exactly which one it is, but it is one that is closest. Another way to see that is if from any point in space I start drawing a sphere that's growing, when does that sphere start touching the object for which I have my signed distance function? That the radius of that sphere, that will be the result. And the signed aspect comes from the fact that the sign will be positive when we are outside the object and negative when we are inside. We can also adopt the exact opposite convention, but the main motivation for this is that we also define the interior and the exterior. So typically we want to represent the exterior of the object and we want to ignore the interior. So before we move to the actual algorithm for this, let's see intermediate cases that are actually not implicit function, even though they look a bit like it. So this is again before GPUs. Dope by Complex in 1995. This is still, it's doing lighting, it has small surfaces, although we can see that the torus is tessellated into triangles because we can still see the straight lines. So this is a large geometry with lots of triangles. It is still not an implicit surface, but it becomes closer to why we need implicit descriptions of 3D objects. This is a case of an implicit scene, an implicit object, but that is still not rendered by remarching. So the object itself, it's actually, you recognized it, the Mandelbrot set. Instead of using colors for the borders of the object, they use z height. So this is a height map. So it's an implicit surface. It's not drawn with triangles, but this still doesn't quite yet require something like remarching, because the rendering, because of the fact that the object is essentially a 2D thing that's elevated, it's actually trivial from one direction to find where we want to look into the object. So you don't need something like remarching to do this. This one starts to be a bit problematic. When you do those kind of fractal objects, so this one is the Menger sponge, or Menger sponge. It's a fractal cube. You can understand the pattern. So here it must be degree 4 or 5, not sure. You start with a cube and you clip holes 1/3 the side of the cube. So here, in the middle, and also actually on the inside. And then you do that recursively. So in each of the cubes that become obvious, that are 1/3 the original size, you do the same thing, and again, and again. So when you want to draw that, you could compute triangles for this object, but that would be a lot of triangles. So it makes sense to search for alternative solutions, and a signed distance function for such an object, it's possible to build one. So now, I wanted to learn how that was done and what are the techniques for this. So this will be only about the geometry. There will be no shading in the examples I have in this presentation. I'm not there yet. I just wanted to understand the geometry. So this is what is explained. So first, a pixel shader will be invoked for every pixel on the screen space, and its point is to compute what is the color that we want for a given pixel on the screen, and it will run in parallel for every single pixel of the screen. So the input that we have are the screen coordinates, and we want to compute colors for that screen coordinates. So very quickly, This is just a change of coordinate so that we have more mathematically convenient coordinates to work with from minus 1/2 to plus 1/2 left, right, and top and bottom scaled appropriately. This is just to have a kind of slowly fading background whenever we don't have anything from our 3D scene object, our signed distance function. And the actual projection of the signed distance function is what is done here. So we have to define what is the camera and what is the focal plane or the focal length that will determine essentially whether the picture will be wide angle or telefocus, tele lens. So here actually it's convenient to just use numbers that are actually in meters. So this is like 36 millimeter and 24 millimeter, like the size of an actual film camera, a full frame film camera. It's just a convention, but it means that everything we will think about will be in terms of, and here the focal plane 50 millimeters, so that will be a standard photo camera lens. And so that means that because I decide to use those values here, everything I will do, it will be like if it was in meters. So for the composing the scene, that will allow me to think about real world coordinates. So that's just for this reason, for this convenience. So this is the screen coordinates that we want according to the projection to this focal plane. What we compute here is the vector that goes from the camera through 1 pixel of the screen. And this is along the line, this line that we want to interrogate our signed distance function. So that's actually the Raymarching algorithm that we will see in the following slides. Sorry, that is invoked for one position of the camera, and each ray that goes through each pixel of the screen. And then, because this is not doing shading, depending on which object will be returned, because this will be which of possibly multiple objects, multiple signed distance functions, is hit by this ray. I will just draw a grayscale for this because there's no actual shading here. So this is what the Raymarching does as a way to interrogate an implicit geometry like a signed distance function. You start in 2D, of course. That's a side cut, let's say, of my camera and a focal plane. So from one origin that's, in our case, going to be the camera, this is the object that would be described by a signed distance function. And this is the direction for the pixel that we want to interrogate the signed distance function for. So at the first object, when we call the signed distance function, we get a distance. That's the distance for the closest part of the 3D object. So it's going to be this one. So that's why we get this distance, so represented by this circle. You will see why in an instant. So we get this distance. That's not terribly useful because that's not at all in this direction. The thing is that at some point along this direction, we will hit the object eventually. And so the Raymarching is a fast algorithm to find along this ray what is essentially the point in 3D space for which the signed distance function will answer 0. 0 distance. That is, you have found the intersection between the ray and the object for which you have the signed distance function. But that can require several steps. So like here from this ray, from this first interrogation, we know that it is at least this far. So it cannot be anywhere along this circle, the actual intersection that we are looking for. So what we can do is safely go along our ray to this the radius we got for the first execution of the signed distance function, and we can interrogate the signed distance function again from here, because we know that the answer could not have been between here and here, because we know that the object is at least as far as this distance. So we interrogate again from here. Because of the shape of the object, we get a smaller radius, so we have to do it again not very far. We have not moved very far. And here, since we, on the contrary, we get farther and farther from the object. That's again because of the shape of this article object. We move along further until at some point when we get here, we interrogate again, we will get a very small number, not exactly 0, but if we put a threshold, and again, if we agree that this is in meters and the objects are some meters from me, I can decide that, let's say, a threshold of 1 millimeter is good enough. And if I make the threshold very small, I will have a few more iterations here for convergence, but it will converge eventually fairly quickly. And there's also, of course, the possibility that it will not hit at all if the object is not at all present along this particular axis. So I will have to stop at some point when I get very far. So I will decide a back distance at which I will just stop. And typically, for safety, in order to ensure termination of the algorithm, there will also be a maximum number of iterations. And those are pretty much arbitrary parameters. They will have an influence of, as an example, what this case would like, which is why in the distance they also put some fog as part of the shading, so that we will not see that maybe the objects are actually hard cut at some point. So in practice, implementation of the algorithm, so this is actual code, except for the sign distance itself. That's the ray marching code. That is really, truly all you need, this function, as long as you have a scene. So let's see what the scene needs to be, and then we will see an example, a simple example of the scene. So a scene typically will be composed of one or several primitives that will be combined. So let's look at one primitive. So for one primitive, what we want to find, if we know how to compute an SDF, it's literally from a given point in 3D space. So that's a vector 3, but it's not a vector in the sense of a direction. That's really some XYZ coordinates in space. And from a ray, so this time an orientation from that 3D, from that point in space, we want to know what is the distance, so that will be a single number, a single floating point number. So starting at point P towards the direction of the vector R, we want to know what is the distance. So we will see an example of a simple distance function. And then, because we want to compose a scene of several SDFs, typically we want to combine several objects, a complete scene is going to be something that returns a slightly more complicated return value, where we still get the distance function if we want to use it, and it's actually useful for shading, even though I will not be doing it in this case. And we want to know which of the objects represented by a number, an instance number, an index in a list of objects. We want to know which one was the closest for that particular array, starting from P towards R. We want to know which object Thank you very much. Okay, so we are back online. Sorry, we had run out of batteries for one of the microphones. So, yeah, I was saying that the total scene is supposed to somehow combine multiple sign distance functions and tell not only the distance, but which is the closest sign distance function. I'm not sure I have sound. Do I have sound? Is the stream hearing? Okay, thank you very much. So the actual remarching, and this is actual shader code, it needs no more than those 5 lines, 6 lines of code. So what this does, we want to interrogate one distance. We want to interrogate along which is the distance along a direction from a starting point. So the starting point is the camera along this direction. We will be searching for no more than 128 of those successive circles, that is 128 interrogations of the scene. And for a given position of the camera, we interrogate the scene. That tells us which object hit at what distance. The distance is component D here from the hit structure. So if it is very small, we found our answer. We found the sign distance function that we were searching for. So we return here in this simple implementation, we return the ID of the object that hit. If we moved very far, if we are now very far, more than 1,000 meters from the closest object, we say that we won't find anything, so we return -1 instead of returning an object number between 0 and the number of objects, the total count of objects we have in our scene. And after we have had one hit, if it was not close enough, if we have not run out, and if we are not desperately far from the closest object, we keep going by essentially adjusting the camera in a way such that we walk by the distance at which the scene is in the direction that we want to walk towards. So we started here, camera here, along this direction. We get this number because it's touching here, this kind of duck, and no, I cannot draw. So we get the answer the first hit is here. So this is the first radius that we get. From here, we get this radius. So what this does is it adjusts this variable that was pointing here, so that now it will be pointing here, because we add the direction vector times the radius that we got. So that is the distance that we need to walk along the ray, which is why it's called ray marching. And that's all we need to implement ray marching. And in case we would start inside, by accident, inside the scene object, inside the side distance function, we will be getting negative distances. So we can also decide to add one line to handle this case, where we say that if we are inside an object, we can't really see anything, so we just exit. So now the question, of course, is how do we build the sign distance function of interesting objects? So this is, I don't know if we will have time for this. Yeah, we have a bit of time. So this is an example. It's actually not the simplest. The simplest thing, of course, is like in regular ray tracing, is tracing a sphere. Because the sign distance function of a sphere is just where we are in space minus the radius of the sphere. That's the distance. The distance of this vector is the distance to the sphere, since when that's the number you want. So for a rectangle or for a box in 3D coordinates, it's a bit more complicated. So first we can make things simpler to explain by looking at the two-dimensional case, because we can see that by symmetry, a box being the same thing as a rectangle but along a third axis, if we can do this in 2D space, it's probably going to trivially extend to the 3D space. So we can see first that by symmetry, if we look at positive x and y coordinates, by symmetry it's going to be easily the same on the other coordinates. And if we look at 1/4 of the object, we can see that there are 3 cases. If we are in this part that is outside one of the borders of the rectangle, but within the other length of the object, what we want is the perpendicular between where we are and the border that will be our closest distance. So here, for the case of sector 1, it will be trivially the x position that we want to interrogate for minus the width or the size of the rectangle in the x direction. And it's going to be the same for this quadrant, except we reverse x and y. So that's why we get those examples. Region 1, the distance will be x coordinate of the point at which we interrogate minus x coordinate of the rectangle. And we, of course, to make things simpler, we say that the rectangle is centered at the origin, of course. So it's going to be the same by swapping x and y for this case. And this one is actually what you already know if you know about what the length of a vector is. It's going to be the length of the vector from this point to the corner. And so, sorry, where did I do that? I did it here. So, yeah. I'm showing you that, and I will go back to the other explanations. So this is the length of a vector between two coordinates, two points into this space. So square root of the delta in x squared and the delta in y, so delta in x, delta in y squared. So now the thing is, how can we make this simpler by exploiting all symmetries so that we compute, we try to find a sign distance function. I wrote the solution here, but we want to understand why this works, and what we are trying to do is a GPU doesn't like to do branches, it doesn't like to do comparisons and so on. So if we can reduce everything out of symmetries and so on to functions that are trivial because they are already pretty much in the hardware of a GPU, like absolute coordinates, like the maximum of two values, but without writing if then else, that will be better for us. So here we want to exploit the symmetries. And if we look at, say, the symmetry of this case to this one, we can see that here the distance, still positive because we are outside, it's going to be this coordinate minus this one, whereas here it was the point minus the rectangle. Here it's going to be the rectangle minus the point. So that's why it's going to be P minus here R, point minus rectangle, Px minus Rx for this case. And here it will be minus Rx, because that's where we are, here, minus Px, because Px is possibly negative, but it is still the correct mathematical formulation. And it's going to be the same for the horizontal symmetry. And if we look at those two things, we can see that the calculation is, what we want to do is swap around. Yeah, sorry, I'll explain from here. Minus Rx, both cases. Here, Px, and minus Px. So if we want to combine those, pretty much what we get is that the distance is going to be the absolute value of P minus Rx. So that's why we can reduce cases 1 and 1 prime into just one calculation. Absolute value of the point at which we want to interrogate, this, minus the width of the rectangle. And that's going to work, of course, in the horizontal direction. And now, if we actually compute both, if the point is here, this is a some distance. If we are here, we know that this length is going to be smaller than the length that we get here. Because this has to be larger, sorry. Because if, no, sorry. It's the opposite. It has to be, this has to be larger. What I mean is that when we are in this region, the x-coordinate is larger than the width of the rectangle, but the y-coordinate is smaller than the height of the rectangle. Because if both were larger, we would be in this region. Which means that if we take this expression for the x-axis and the y-axis, when we are either here or here, what is going to be true is that the largest of those two calculations is going to be the right one. So if we do maximum of those two calculations, the one for the horizontal case and the one for the vertical case, maximum will be the right number. We don't know which one wins, but we don't care. All we want is the length. So this gives us the right number. So this actually reduces. So now all those four cases reduce, and by symmetry, actually, sorry, this one, same here, and this one and this one. So everything except the diagonals pretty much reduces to just this expression, maximum of absolute value of the vector calculation minus the rectangle width and height. So again, something that the GPU can compute in just one statement. So now, how do we combine this calculation with the case where we are more in the diagonals? So when we are in those cases, this holds. That is, 1 of x is larger, but y is smaller, or the opposite. It cannot be both. So, so that was for case 1. That means that, sorry, let me see what I'm doing here. That means that when I am in this case, the distance is going to be this case. This is the winning case, not the one along y, which means that if I also take py minus ry, it's going to be a negative number. And what I would want to do in order to turn both calculations into just one is use something like maximum of 0 and this negative value, because that will also give me 0. And if I add it to what I calculated, this still works. This is still my px minus rx, which is the right answer. So that means I can also do arbitrarily this transformation, and the calculation is still correct, because this is the only non-zero number. This will be 0. And why do I want to do this? Because it looks like the case of the third situation, where I use the Euclidean distance between the corner of the rectangle and my point at which I want to interrogate. So why am I doing those transforms that don't change anything to cases 1 and 2? It's because now I have an expression that's pretty much the same as what I get for case 3, and the point is to have a single expression that works for everything. So this is what I do here. So I take the calculation from case 3, this one, and it's actually the same expression computed this way. Maximum in the x and y distance between 0, so that I get rid of negative numbers, and the calculations along the x and y axes of absolute value of the point at which I want the sign distance function minus the corner of the rectangle. So this is actually the expression I get here. That's the justification for writing this equation as the sign distance function. Now, so I will go quickly. I will skip this one, because otherwise we are going to run out of time. This additional calculation is that we also handle the case where we are inside the rectangle, so that we also get the negative values of the sign distance function in case we would be inside the object. So I will skip the calculation. So the motivation of doing it like this equation for the sign distance function of a box, of a rectangle, is that this one works, and it is exact. This is the exact distance to the rectangle, or to the box in 3D coordinates. And that's because of the definition of the Euclidean distance. And it's convenient because when we want to do things like computing normals that we will need to do some shading and some lighting, we want to have exact distances. There is actually a simplification, and sometimes it's convenient to work this way for sign distance functions that are hard to do for some type of objects. It's to use something that is not the Euclidean distance, but the L infinite norm, where essentially we take the largest of the distances along the x or y or z axis. So like on a Manhattan graph, where we go only along verticals and horizontals, we just get the smallest of those the largest of those distances. And the reason why this will work, and it's a simpler calculation, you can see here, this is simpler than what we had here, it's because we still get a distinction of what is the closest object among multiple objects. And essentially, this does a distance sorting. It will sort objects by distance, and it will find the closest objects if they all work with an L infinite norm. The one thing you cannot do is combine Euclidean distance and L infinite norm. So this is pretty much what you actually get when you do the infinite norm of a box. For a given point, you get just the furthest, the largest distance you have to walk, like this, in order to reach the corner that is the closest to you, or the side, depending, or the facet, by walking along the axis of your 3D space. Instead of computing the Euclidean distance, that would be the direct, the straight line between the 2 points that you want distance between. So when we want to combine a scene, we can do something like that. So this is a simple case. Again, just a few lines that actually work in the shader. So here it's a combination of 2 boxes that are composed of our box equation from earlier, for which we just put some sizes. And so this one, the whole point is just to have it move in space by rotating its position. So by transforming it through a rotation, I will not go through what the rotation does, but this is the same thing as in any geometry that has been done since 30 years or 40 years. And all we do is compute the sign distance function for each of those boxes, and we just check which is closest. This is our answer. That's all we have to do. So again, pretty much 1 line per object that we want to add in the scene. And the object can be located in terms of resizing, rotating, and translating by just adjusting the apparent position of the camera in reverse. So we do a reverse transformation from camera to object, and that essentially means interrogating the object from a camera that is now at a different position. That's the same thing as interrogating an object that is at a different position from a fixed camera. So literally, this kind of example, and you can check the example code on ShaderToy, it will look like this, like the box in the middle, and the ones that rotating around, so we can see that it is going to be correctly perspective projected, even though there is no shading. That's why I chose this angle, because this is not doing any shading, it's just doing different grayscales to distinguish between the 2 boxes. So again, this of course needs shading, but this was just for the point of understanding the geometry. So that's pretty much all you need to do a ray marching of a sign distance function. So now we'll just give a few references. So first, a lot of these things have been apparently not invented, but put into very nice and didactic and presentations by this man, Inigo Quiles. He works from, I don't remember which of the 3D cartoon companies, DreamWorks or Pixar? Sorry, Pixar, thank you. Yeah, probably Pixar. And in particular, what is very interesting on his website is that he has a collection of signed distance functions for many elementary geometric objects, and how to combine them with, in particular, constructive solid geometry. So like when you want to do an OR between 2 objects to merge them, or an AND to make a whole, make the intersection of 2 objects, or you can do a subtraction to make a whole in an object with another object. So he has equations on how to do all those combinations. And this scene comes from an example from him. This is not geometry at all. This cartoon character is entirely done with sign distance functions by deforming ellipsoids, egg-shaped objects, and doing essentially not replications, but periodic extensions of an object by just clamping and the coordinates at which the object is interrogated. That creates a repetition of the object without adding any geometry. So each of the dreadlocks are a single primitive on which a camera coordinate transform is applied in order to make them periodic, to make them repetitive, essentially by doing a modulo operator on the coordinates at which we interrogate the object. So I encourage you to check the code. This is this example, and it's quite impressive. It's really not that many lines of code. Of course, there's additional code for the shading, but for the geometry, it's impressive how he does that. There is another good tutorial that also explains basic shading by this guy, Michael Volchik, that I encourage you to check out. The shader itself is written in the GLSL language, even if you do that directly on the web with WebGL, which is what you do in ShaderToy. So you write just those few lines of code for the pixel shader. That's the language that you need to know about, at least the basics. So again, what I showed here, this is actually GLSL code for WebGL, so inside ShaderToy. And you could do that directly with your own JavaScript, and you can also do it in p5.js, which is a bit like processing, but in the browser. So it's really nice. And there is an alternative to ShaderToy, which is Posh Broly, which is also very good.
Yeah,
that's your project.
Yeah.
You're the man. You're the man. Come in front of the camera. We can see you. So that's the man.
I made Posh Broly. Yeah, I'm so proud. Oh, thank you so much, man. Use it. It's great. It's fun. It's beautiful.
It's
nice UI. Oh my God, nice UI.
It's actually better and more reactive, instant than ShaderToy.
Oh, I'm so humbled. Thank you so much. Thank you for mentioning me in your talk. I'm humbled. Thank you.
So, and just for the bibliography, where this comes from, Algorithms by John Hart. He called that sphere tracing initially. So you can see it's from the 90s. And also there are early uses of pretty much the same techniques, in particular in how to do procedural texturing, 3D textures by Ron Perlin, that you may also know for the Perlin noise, and many ways to get repetitive motifs with not a lot of calculations. The Wikipedia article is not that bad, actually. A catalog of excellent demos, early demos, and some good demos that have a good use of repetitive, periodic SDFs that would be completely impossible with triangles with explicit geometry. So you should check out those demos if you don't know them. That's it. Thank you very much. If you have questions. So if you have questions, and we will make the slides available somewhere on the Shadow Party stream if you want to read again the calculations, the derivations, or check out the links. So, questions, anyone? No questions? We're good? It's warm in here. I'm sweating. No questions? Okay. So, the stream will pause. Thank you very much. Bye.